So, yeah, thank you very much. Good morning and good afternoon, everyone. I think we have already people joining us across the globe. And thank you for joining us today. And we are happy to welcome you to this session. Uh, as the your biomanufacturing evolves, right, the expectations also increasing, from achieving higher yields to accelerating batch release and all that while staying within the limits of compliance and quality, right? So we will discuss about tools like your process analytical technologies or your advanced analytics or advanced control strategies, right? And understand how these kind of tools are helping us to meet these expectations, right? So whether you are an engineer in operations or you are engineer in process or an engineer in automation or a team member in your digital transformation, teams, right? So this session can help providing, some practical insights. So with that background, let's quickly deep dive. Okay, before we dive in, a quick introduction. My name is Malaya Chittimalla. I'm one of the strategy consulting lead for life sciences manufacturing at Cognizant, which is part of our broader industry solutions group. Basically, I'm a chemical engineer with over 21 years of experience. I started my career in a process industry, handled roles in process and operations before transitioning to IT industry. And since then, I've been part of many digital transformation initiatives for our clients globally. Aurelien, over to you, please, for a quick introduction.
Yeah, yeah. So my name is Aurélien. My career has been dedicated to pharma. So studied pharma, applied pharma. So studied in manufacturing, managing production lines. Then a deep dive in automation for a good duration. Then MES. It's been a while. I've part of the life science manufacturing group consulting team where we help our customer answer different type of questions, such as what PAT, as an example, as for today, or it can be application landscape overall for new plants, product selection, and so on. So I'll go back to you, Maria.
Yeah, thank you, Aurelian. So here is what we will cover in today's session, right? So we will start with understanding the bigger picture, right? Starting with some of the key industry challenges to those operational KPIs, right? To those operational KPIs and how the KPIs, operational KPIs, link to your corporate or enterprise, level KPIs. And then we will discuss the key like CPPs for the fermentation operations, right, which drives the fermentation performance and various control strategies that optimize these parameters in real time, right? So the topics one and two essentially sets the foundation for our discussion going forward, right? And from there we will move on to the process analytical technology overview. We will take Raman PAT an example, and we'll look at various components of the PAT architecture and understand its role in the deeper and richer process understanding. So we will also look at one of the real time real life use case from your measurement to all the way up to your advanced or feed forward controller action. So from there, we will also explore a value model for PAT implementation at any factory. And finally, we will wrap up with a Q&A. So feel free to note your questions for the slot that we are dedicating for this purpose, right? So let me take a moment to align, right, what you can expect to take away from this session, right? So by the end of the session, you will be able to understand or articulate the business impact of your fermentation efficiency, right? This is not just optimizing a process in isolation. It is essentially driving those broader business outcomes. and then understand how these CPP CQS interact, and what kind of control strategies are evolving, right, from a traditional your PID loops to more intelligent and feed forward mechanisms, right? And then you will understand, you will come to know what are the different components in end-to-end PAT architecture. We will present you one example PAT architecture, right? And how they interact with each other, right? And then finally you will also understand how to move away from a concept theory to a business case, right? An illustration how to calculate your returns when you implement a PAT kind of solution, and then how you have to present it to your decision makers, right? So the goal is to walk away not just with technical insights, but with some strategic framework you can bring back to your teams and operations. So this is the objective of the session. I'm just moving on, right? So quickly, I'll be covering the industry challenges, right? You all know, right? The expectations from the patients, the regulators, and society in general changing rapidly when it comes to the medicine, drugs, and all, right? So the industry must evolve with that, right? So speed to market, right? When I say speed to market, patients wants the treatments faster, right? So the industry has a responsibility to deliver those medicines, bring those medicines to market quickly, right? The demand is ever growing, so we need to meet the demand by, again, optimizing our efficiencies, producing better yields, and so on, right? Costs pressures are always there, right? So we need to make the medicine affordability. That means that we need to cut costs and produce again efficiently, right? Sustainability by design means, again, this refers to consuming less water, energy, reducing waste. A lot of net zero initiatives that we see in the market today, right? So most of the modern factories that are coming today, right, they are state of the art factories, no doubt at all. But what we need is a smart factory, with the smart tools which support us in all these business drivers, right? So that we will transform, run our operations faster, better, and leaner, right? So that is what these tools are going to enable. So those industry-wide challenges, right, we just discussed, they are not in isolation, right? They are not theoretical. They are actually shaping up how the industry is setting up their KPIs and chasing their KPIs, right? So let's understand from a simple fermentation process perspective, right, how that can impact an enterprise level your financial outcomes, right? So at an operational level, right, heart of the manufacturing, right, we usually have the KPIs for yield, cycle time, your waste and productivity, and so on, right? So every batch for our from our fermentation, right, that hits the targets on these KPIs, right? That particular batch, right, uh, accelerates the time to market of our product, right? The commercially available product, right? So which improves the working capital turnover, right? Which adds some quicker revenues, right? Again, minimizing the deviations, keeps our operations cost very leaner, right? Improves our OM at a BU, or improves EBITDA at enterprise level. EBITDAs, usually they are calculated by reducing your expenses from the sales revenues, right? In the profit and loss statements. So improving these operational KPIs, is very essential. What we need is a connected and more smart, technologies for understanding our process better and controlling our process better, right? So this is how we drive the impact. So next time when you guys are analyzing any batch failures or trying to optimize your glucose injection strategies, right, just remember that you are not just isolating or optimizing that steel vessel in isolation, right? Basically you are driving business impact. So with that background on business, right, let's start with our fermentation process. Let's come back to our topic. So So let's understand some of the key CPPs that govern our fermentation process, right? So these parameters play a very crucial role in maintaining that process consistency. We all know, right? So temperature. Any fermentation process that is highly sensitive to temperature, it affects that reaction growth kinetics, right? Usually a robust jacket control mechanisms are employed, right, to eliminate or avoid that thermal shocks, right? pH, maintaining right pH again is very essential for your cell growth and cell metabolism, right? So we control it by your acid or base dosing pumps, right? Again, there will be inline pH probes and feed forward control loops to maintain that flow rates, right? Dissolved oxygen again, which is another important parameter for the aeration, for the aeration fermentation processes, right? So the cells use it for respiration and productivity. uh, Usually we control this by agitation speeds or your sparger airflows or sometimes direct oxygen supplementation, right? So devo is again tightly linked to your oxygen uptake rate and metabolic shifts, right? Agitation speed, right? Again, this is another important parameter. You need it for mixing efficiency. You need it for proper gas to liquid mass transfer, heat transfer, and so on, right? So if the speeds are very high, it can cause that shear stress, and then shells could damage, right? So maintaining the speed is again an important parameter. Aeration rate again controls that oxygen transfer. Inoculum density refers to your viable cells that is introduced to your fermenter, right? This determines how quickly your biomass can accumulate, right? Again, coming to the glucose feed rates, right, which is very essential, right? To eliminate your or to avoid your overflow metabolisms or your nutrient shortage kind of scenarios, right? So your recipe parameters control this. Again, foam, which is an unwanted scenario. Again, it could interfere with your sensors. It could create contamination problems and all. So again, sensors will control that anti-foam injection rates. So apart from managing and maintaining these CPPs, right, we also track certain quality attributes to see, right, whether our product meets that safety, efficacy, or other regulatory requirements, right? So again, potency refers to how well our product performs biologically, right? It's a functional CQA tested post harvest, right? Things like receptor binding or generating required immune response, like it refers to that, right? Things like your pH, dissolved oxygen, or shear stresses could influence the potency, right? Again, purity. Purity refers to how clean our product, free from all those host cell proteins or DNA, things like that, right? So we need to maintain that viability, and then control that lysis so that our products is free from all those host cell proteins and so on, other impurities, right? Similarly, all these things, right, these are certain quality attributes will be influenced if you're not managing properly these CPPs, we all know, right? Let's focus on the glucose here, because or discussion going forward will be totally focused on the glucose feed rate, right? So glucose, I would say, it is not just a nutrient, it's a control lever that we have, basically, right? So managing the glucose feed rate precisely is very important, is very essential to maintain a healthy, productive your fermentation environment, right? So a deviation here is not just causes a metabolic shift, but it can cascade into your product quality attributes, right? So let's look at overfeeding, right? So when it when we introduce or inject more glucose than required, right, it can lead to your overflow metabolism. Means, right, instead of converting the glucose to CO2 via a TCA cycle, right, the cells will find a shortcut to generate energy, right? So the shortcut could be, right, they convert this excess carbon to your byproducts like lactate or acetate kind of byproducts, right? So that situation we need to avoid. And when the cells feel a nutrient starvation, right, its behavior changes, the growth will arrest, it starts multiplying. So it enters a stationary phase, right? And if there is a prolonged starvation, it can lead to a cell death also, right? So this is how this particular character, right, the glucose has to be tightly controlled, and we need to definitely move away from a reactive to predictive control kind of mechanisms, right? So let's quickly, with that, background, right? Let's quickly look at, some of the control strategies that we have today, right? Just imagine, right, yourself standing in front of, in a GMP clean room in front of this kind of your fermenter, right, with limited instrumentation, right? You don't have any real-time data. You don't know what is happening behind these steel walls. There could be metabolic shifts happening. There could be lactate or your byproducts accumulating. That is the reason your batch yields swing like a pendulum between different batches, right? So traditionally, with such kind of systems, right, your operators manually withdraw samples from your fermentation broth, transfer it to lab, and then lab has to analyze using their own techniques, and again communicate the results to you. Right? Then only you take an operators used to take actions. Right? So this means that any change that is required in your glucose input, right, is reactive. It's based on the past data, not based on the real time insights, right? So limitations, there is a time lag, there is contamination risk, there is it's labor intensive, and there is no real time feedback, right? So you are all quality is known after testing in the lab only, right? So what we would need is an automated strategy with powered by real time data. So that is what your these kind of tools are going to enable. You see, the modern approach, right? So the modern approach is essentially they are using the PAT and quality by design kind of principles. You know, so imagine the same, bioreactor where you are standing in a GMP clean room, right? So now that bioreactor has all the instrumentation, right, and it talks back. We are not basically waiting for the problems. We are going to prevent. So the process is not controlling. We are going to control the process, right? So with the inline sensors like RAMAN PAT, right? So right inside the vessel. Uh, Making measurements within the fermentation broth, right, and these measurements in real time when it is cascaded to your chemometric models, right, these measurements will give you the component attributes of your vessel, right? So that those models will interpret that complex spectra data to estimate the concentrations, right? You don't have to draw any sample from this vessel. So that is what your inline monitoring. So online monitoring, we have not come across much in the life sciences business, but they are popular in other industries like food and beverages. They usually draw a sample in a bypass loop or in an external loop and uses these biosensors to detect the concentrations. But here, anything, right, other than your offline, right, inline or online, you see there is no delay. Okay, online is not that as fast as inline, but in general, there is no delay. There is no sample transfer required. There is no contamination risk. It enables your your fully automated control, right? So this is what the difference in the modern approaches. So let's look at some of the basic control concepts, very basics, right? Manual. When it comes to manual, you have a controller, and then you give a set point to the controller, and that controller goes on maintaining that set point unless manually you change this set point, right? Feedback, it's a very classic control loop, widely used in many control loops, many parameters control. What it senses is it senses a process variable. It measures a process variable of a process, and then compares with a set point, and the error, the difference, basically in the control language they call it as an error. Your controller looks at that error and basically makes an adjustment in your control wall. Final control element is your control wall. Manipulated variable is the opening of that particular control wall. So it changes the opening of your control wall, basically that input to your process. So if you look at here, right, feedback controller senses the change in the process value, which means the process has already impacted, and the process value is either reducing or increasing, right? That difference is known here, and then you take an action. So again, it's a reactive. So when it comes to feed forward, right, feed forward is something exciting, is an advanced control strategy. It senses the disturbance in the process, right, and it overrides the signal that is coming from your feedback controller. So it takes an upfront action in the process so that this disturbance will not reduce the your process value, right? So even when the process value is managed, maintained at the required set point, it could take an action because your disturbance in near future, it is going to reduce it. So it makes an upfront action to so that disturbance will not be impacted in the process, right? So these are some of the basic control strategy concepts. So with that basics on, now we have seen the basics on fermentation, parameters, and basic control strategies, right? So let's look at what this PAT is, right? And let's look at these components of the PAT, right? So we have Raman probe, which is nothing but a sampling interface. This is the one delivers the laser light to the sample and collects the scattered light from the sample, right? Which is generally inserted directly into the fermenter, which is inline probe. There is a fiber optic cable which connects the probe and the analyzer. Analyzer houses the laser source, your spectrometer, and there is an embedded controller and its software, right? So laser source sends the laser light with the required wavelength. It depends on the sample type, and the spectrometer essentially, it separates the collected, scattered light into component wavelengths, generates a spectrum that shows the intensity of Raman shifts, which corresponds to the corresponding molecular vibrations in the vessel, right? And this software essentially, it can pre-process that raw spectra data that is collected, and then convert to Raman spectrums, and send. This is the one, it can interface with your process control systems, or the PAT orchestration tools, right? uh, just moving on. So PAT plus chemometrics, right? So the output from PAT, so we know, right? The input is the raw spectral data. So the output from the PAT analyzer is essentially the processed signals. They are they are the Raman spectrums, intensity versus Raman shift, right? Which essentially presents the unique fingerprints of the molecules that present in the fermenter, right? So that goes as an input to your chemometric models, which are mathematical models, the statistical models, which interpret this molecular fingerprints into your molecule concentrations. So that is how your raw spectral data is converted to your concentrations by the chemometric models. There are different modeling techniques available again to build these models. So in summary, right, the PAT provides you the deeper and richer understanding into what's happening inside the fermenter, right? So you will get that real time insights into biological variability, right? So fermentation inherently it's a very dynamic process. Hour by hour your conditions are changing, right? So these tools uh, will allow us to measure the parameters without actually waiting for your offline samples, right? So it enables your visibility into process. It enables you to take a data driven decisions, right? Basically we are shifting from a scheduled based actions to your condition based actions, right? So that is how PAT enhances our fermenter process understanding. So now let's see, how we move from this real-time component information that we are getting from your PAT tools and your model chemometric models, and how we use this information for generating that advanced feed forward control signal, right? So what we need is essentially a digital twin of the fermenter, right? With the twin with your mechanistic models and the state estimation models. When I say mechanistic models, they are the engineering models, essentially the engineering twins of your fermentation vessel, right? So unlike your pure mathematical models, they use the engineering principles and science. So they use your mass and energy balance laws, they use your heat transfer laws, they use your reaction kinetics, they use your thermodynamics. So basically you model your physical fermenter. So we do have for cell culture modeling, we do have some techniques, scientific techniques. We have some engineering equations like Monod equation, or there are some other equations like PERT models and all, so that you can build that engineering model of your fermenter, right? Which can detect you, which can give you, in the engineering terms, right? You call them as XTs, STs, or PTs, right? These are the concentrations of your substrate, biomass, or your product, right? At any given time, right? And the rate of changes of these things, your dx by dt, ds by dt, or dp by dt, they are all ordinary differential equations, and the whole modeling is an equation oriented modeling, okay? So when that particular engineering model, when we input with the real-time data from our historians, right, all the sensor data, all not all, whatever required sensor data, like your concentrations or your capacitance, probe data, or your off-gas pattern data, right? So this becomes a digital twin for you, and for predicting the future state, right, or I would say, like, for refining a future state, uh, we have again another state estimation modeling with equations like Kalman filter and so on, right? So we employ that model over and above your engineering model, so that you will have a refined state estimates, right? And that refined state estimates and uh, your desired future state. For example, you may want to say maintain a glucose feed rate of say zero point 0.8 or 1 gram per liter, right? And your optimization model, which is nothing but a MPC kind of model, takes that inputs and your constraints, something like your maybe feed pump specifications or feed pump constraints, and it takes constraints, it takes the future required state, it takes the real time current scenario, and it will try to solve an optimization problem, right? So it will ask the mechanistic model, okay, if I continue dosing say certain amount of my glucose, right, how would my process looks say in next 30 minutes, right? So that is how it performs a lot of simulations with your engineering models, and finally it arrives on a optimized feeding strategy, right? We call it as an FT. It's a feeding strategy, and that revised or renew new feeding strategy will be fed back to your control systems, right? So this is how the end to end loop works, starting from measurements all the way to change in glucose injection rates, and finally download it to your control systems, right? So let me quickly explain this. What kind of changes required in the basically control loops, right? Left hand side, you see your traditional control block, right? You have a transmitter giving a 4 to 20 milliampere signal to your controller, and then controller gives its output again in 4 to 20, and which goes to an I to P converter, right? And where you convert to a 3 to 15 psi signal. This is a pneumatic air pressure, right? It is standard any control loop. So when you employ your PAT with an advanced control strategy, right? So you take a feed forward signal. You need to make certain changes in the FIC function block to take this input. And what you need a selector switch here. What we see how our clients are implementing this in two phases. In the phase one, essentially they want to see it. It's in manual mode. They want to see how much signal, how much change it is making, and they want to manually change the set point here. And in phase two, once they build the confidence, right, they take it in auto mode, and it automatically overrides the signal coming in from your feed forward feedback controller, and then the actual signal that goes to controller is to the valve is from your models, right? This is what this is what in phase two that that they are achieving, right? So yeah, coming to end-to-end system architecture, right? So again, there are different ways to design it, and this is one of the method, right? At level one, right? If you look at the ISA 95 hierarchy, right? At level one, you have the Raman probe, you have the Raman analyzer, right? And at level two, there is something called PAT orchestrator, okay, which is a very important component in the overall architecture. So at level two, this PAT orchestrator is integrated with your process control system via OPC-UA. Again, even this interface is via OPC-UA, your analyzer to PAT orchestrator. So at level two, the orchestrator takes the recipe values, when to start data collection, when to stop the data collection, from the system, right? So it takes that recipe parameters and downloads all the way up to your probe, and as per the recipe requirement, it collects your spectral data. This particular piece, the analyzer, it converts the raw spectral data. There are certain pre-processing happening in the analyzer. It whatever the processed spectrums are given to the PAT orchestrator, right? So here the PAT orchestrator, right? This is where our chemometric models are sitting, right? So the models are built at a level 4 modeling platform, and they're all downloaded, deployed onto your PAT orchestrator platform via proper model management and version control things, right? So but the models for us are sitting at edge on the orchestrator platform. So these models, they take input of this processed spectrums and convert them to your components information, right? So that component information with other alerts or notifications, that is given to your DCS control systems or historians as required, right? So this is, until now you have the component information available at your control systems. So now you need to feed that component information to your digital twin, which is again living at level 4, right? And the digital twin, which is nothing but you have an engineering model, you have a state estimation model, you have a MPC model predictive controller there, which gives you a revised feed strategy that again you will take it back all the way up to your control system. You will download it to your DCS control system, right? So usually this happens, see, in the past implementation we have experienced it via historian. There could be other methods for integration. If you are using an OSA Pi, this integration happens via an OSA Pi integrator, and this happens via an OSA Pi web API. Again, this is an OPC. You will download it to your DCS control, blocks, control modules, right? So even a similar way, the digital twin models are built and deployed here. So these are the offline models. If you need any information for your offline model, training, fine tuning, and all that data usually downloaded in an offline mode to your offline models from your historians, MES, or LIMS, whatever data that is required, right? So that you download and give it to your offline model tuning and training. So once again that models are updated through proper model revision, approval things, you again deploy them back to your live environment, right? So this is how the overall architecture looks like. You see the beauty of this architecture. You have traditional your control systems involved, your level 4 data, your digital twins are involved, data lakes are involved, and then you have the analytics involved, which are nothing but your mathematics based statistical based multivariate analytics. You have an engineering analytics involved. So that is the complexity of the system. And again, you have an IT OT network integration happening here, right? So all that network segmentation, cyber security aspects coming in picture. So that is the complexity of the system here. So I'm just moving on. Okay, we have already discussed this. Usually, these analyzer softwares will interface with your DCS systems or any other PAT orchestration tools via generally via OPC. If it is if it is little older systems, you can also integrate via Modbus. But that is how they integrate and exchange the data in two ways, right? Coming to the summary of the components, right? Uh, it's starting with the probe, right? Probe is considered as eye because which it sees the sample, right? Probe is considered as eye, and then analyzer is considered as the brain because it processes what the probe sees, right? Orchestration platform, which is a very important component in the end-to-end architecture because it coordinates a lot of stuff and runs that chemometric models, right? So when you have multiple production lines, multiple fermentation vessels, right, multiple samples, this is the one coordinates all that and selects proper models for proper samples and so on, right? Then chemometric model, we discussed it. It processes that raw spectral data and not raw spectral data, the processed spectral data, the spectrums, Raman spectrums, and converts it to your component concentrations, right? Digital twin, we discussed. These they are the engineering models. Model management again is an essential because this is all end to end is going to be a GMP validated environment. So version control is very important here. Then yeah, we looked at different models that are available. I'm just moving on. So I will quickly touch, how to build a business case for PAT implementations, right? And how to move away from a, concept to, a business case, a value model, and how you should present it to your decision makers for budget approval, right? So this is the value model typically we use. Left hand side, you see we have a use case here, and the business drivers map to this particular use case. You have speed, revenue, cost, and some cultural aspects, and you have the value levers, right? Asset productivity, supply productivity, your process productivity, right? So PAT tools essentially optimize, these value levers to drive the business impact on these parameters, right? So the left hand side talks about the business, right? And the central part here, if you look at the central part, right, you have uh, the KPIs and metrics that you can have some targets against which, right? So you have your KPIs like yield, cycle times, your operating costs, and your how fast you can move away from a process fit to NPI, right? So things like that, your how deep and rich understanding of the process that you are going to have, right? And things like that, your release time and all that, against which you can have some targets, right? You can see here, typically we see the a percent target of your yield, or a percent, or reduction in your cycle time for your commercial launch, right? So these kind of targets that we see. And right hand side, you have things related to your technology implementation, right? So these are all the implementation factors, and these are all what kind of digital or technology foundations that you should have in order to implement these kind of systems, right? So if you closely observe the implementation factors here, it has a high complexity because you just saw the architecture, right? What level of complexity it has. But when you come to the technical risk, right, the risk is low because you have experience in the market. So we've been implementing, from, so you will find your partners who has implemented such kind of systems, right? And analytics again is getting matured, right? So there is low technical risk but high technical complexity. And organizational risk medium because it needs certain, when it comes to training aspects or change impact, right? People needs to be educated and explained, right? That's the reason it is medium. And timeline usually it takes a good amount of time. It's high. And the cost also, it could a double dollar t-shirt kind of sizing, right? It can take up to 1 million budget, right? So typically these are the implementation factors that you should consider when it comes to the digital foundations, right? So obviously you need all your manufacturing systems, but what additionally you need is the modeling platforms for your chemometric modeling and for your digital twin modelings, right? Your state estimations and MPC modelings, you need platforms. And what you additionally you need is an integration platform for publishing and subscribing to the messages, and then finally you will have a level 4 data lake, right? So these are the kind of mm, foundations you need, right? So this is how on one slide how you can present the entire picture, starting from your business objectives to your KPIs to your technical parameters, right? So moving on, right? This slide presents an illustration, right, of a cost benefit summary, right? Various cost elements, right? Again, this could be for one site. You will have various cost components, and you so this is again another classic example where you have all OT hardware, IT hardware, your softwares, right? And then you will have all services, right? The services could be an integration services, it could be a model development services, right? So all putting together, it can go up to 700K to almost 1 million dollar budget. So it's expensive, but just let's look at the benefits, right? Sorry. So you need to collect certain baseline base year information, right? Just assume that you are producing 55 batches in a base year, with an average yield rate, 25 grams per batch. You just see in the base year, you are you know uh, there is too much deviation here, right? So minimum in a batch you are producing 20 grams per batch, and maximum you are producing 35 grams per batch. So the yields are swinging like pendulum for sure here. So the total grams that you produced here is this much, and 1375, and cost per batch, from the base year, right? It's approximately 30 and 300K, including all your material costs, labor costs, and your overhead costs and all. So this is how you can collect certain baseline information from your finance department or operations department. And once the PAT is implemented, right, assuming that the production demand is the same, production capacity is the same, right, and with the same average cost for batch. So this is the just high level calculation. We can even have a very in depth calculations, but at a high level, if you see post PAT implementation, assume that, not assume, this is what we are actually seeing in the market with couple of our clients. You see average grams per batch, if you are consistently managing at this level, from this level, right? So 20 to 35, at least if you are managing consistently at 30, to produce the same you will have to produce only 45 batches, right? Not 55 batches. So 10 batches you are avoiding or eliminating, right? So again, which has you are eliminating certain costs. So in general, right, what we see here is the payback period is not years or years, right? It just few batches of that particular year, so you can recover the entire cost, right? uh, you see that is the business impact of these kind of tools that we see in the market today. So with that, I have completed my uh, discussion, right? If we have any questions, we can discuss. Obviously, we couldn't cover in depth because of the time availability, right? But you can pass the questions to ISP or to us. We are always available, to answer your questions. Yeah, with the 45 minutes time given, we couldn't go in depth, right? So, but I tried to cover the complete concept of this optimizing batch yield using tools like your PAT and advanced control strategies. Yeah, sorry. Any questions? Anyone?
Thank you, Malaya. Aurelia, do you have any comments or questions that you received?
There were questions from Osam. I try to reply. So I mean to reply to the question verbally. So as mentioned by Osam, mathematical model are inherently not accurate. There is many parameters and multiple dimension. Those mathematical model need to create more than 3 dimension to go to the results. So it's obviously complicated to go to the accurate level. That's why there is a huge effort with regard to training the model to work within design space. So as when I was presenting, the development effort for this model is almost half of the budget. He was showing 300K out of 700 plus, So scientists need to really put the data together with the right model, with the right tuning to get to the level of accuracy. And then,
Just I want to add one point really in there. So that's the reason that two level of implementation is happening, right? So yeah, uh, because of uncertainty, right? So obviously you reach that stage in two steps. The step one, you have a selector switch there in your control system. You basically look at what the model is suggesting and then take a decision there. The step two, when the models are matured, you have enough confidence, then everything happens automatically without any operator intervention. Yeah, go ahead, Aurelian. Yeah.
I mean, yeah, which is exactly what I was mentioning to the chat. It's good we agree. So yeah, essentially the idea is at the beginning you go with a net instead of getting a direct control of your set points on your feed rates. You get a human to check that. It can be through a prompt, and mostly it is through a prompt that you get on the graphic that we see clients implementing that solution. It can be through equipment module steps that will ask you to confirm the change of set point as an example. And after a good amount of months and batches, then people can go without net essentially and let the system on its own. But again, validation is crucial. We are not looking at systems that are self-learning. That is a key points. We are looking at systems that model that are version control. When we are happy with the outputs, obviously they are not moving anymore. So we avoid any self-learning algorithm for sure. All of that should be version control and validated. Yeah.
So thanks to Hossam for that question. We have a question from Sushanth. Thank you. Could you brief on the digital twin concept? Does that mean complete replica of the physical system?
All right. So on the digital twin, there is different type of digital twin. Sorry, there is the physical, the physical representation of a system. So we are looking at the entire the entire factory where you can see where are the goods, where are the equipment. So those are more like the physical setup. Then there is a chemical digital twin where we see where is an equipment. So you have all the CQA, you have the CDP, you have a really chemical and biochemical representation of the system. You also have scheduling digital twin, which is more state of your assets. But here by digital twin, we are looking at the chemistry representation of what's happening in the reactor. And so there is different type of use case. Essentially, when you are looking at complex calculation that needs data from different systems, we are typically seeing digital twin at level 4, where you have all the data coming from historian, MES, sometimes ERP, if you are looking at information from a raw material uh, specification, essentially. Then you will feed that into a digital twin, and you have this predictive model running in that twin, feeding that back to the floor. So that comes with a longer validation experience because obviously the architecture that you utilize it is a bit less exposed to GMP. Typically, IT is a bit less validated environment. And obviously, the route of the data is longer. You have more pipeline to validate. But we are utilizing digital twin for more complex model. So all the model that are more spectral database only, where you are really happy with the Raman spectral data, your model is integrating that and getting you an output. You don't need to go all the way to a digital twin. You can keep it simple to get the most out of it. So that would be probe to analyzer to orchestrator, and that's it. It is simple. It stays at level 2, level 3 in your S95 architecture.
Thank you for that. We've got a question from Amit Kumar asking, looking at the high-level architecture, is the entire solution to be a multi-vendor solution? at least the PAT orchestrator, digital twins, etc., managed by different vendors?
Yes, so at the moment, I mean, we see key players on the markets which are pretty good at the orchestrator, where the model lives and runs, and those players tend to have a good platform for modeling as well. However, from a pro perspective, you have the usual suspect, and they are not the same vendor as the orchestrator. So you really have, for now, not a full package from a vendor. So you go typically with multi-vendor. Specifically on the modeling, something we never seen, or I don't think we'll ever see that in the coming 10 years, is obviously scientific have their own use case and they utilize different modeling systems. So it's typical to see organization running 5 to 10 modeling systems because of the chemical use cases. So all of that need to funnel down back to your orchestration platform. And that is what is really important. So go with multi-vendor on the modeling system, but then at the enterprise level, try to find an orchestrating system, an analyzer system that works throughout the entire organization. Because
Yeah.
it going wild with the application count. We are seeing that often actually, and the cost of ownership that get too high, it's too much to manage.
Thank you. The next question is how to avoid weak signal from Raman. Could you please explain?
Uh, I'm not too sure about that. Can you give more detail about that? Is it like a weak spectral data coming back from the probe? Is that the question?
Wait for the reply.
Otherwise, in the meantime, we can take another
If you
because
could
I'm
help to clarify your question.
yeah
In the
yeah.
meantime, there's a question from Amit who asks, how are these models validated?
All right. So essentially, to put Malaya at the beginning, we are looking at quality by design as a base. We really want to link our CQA to our CPP to our process control functions. So that's the framework that we tend to use. And then, from a validation perspective, you obviously have the entire setup of application. You need to get all your architecture, your network, all of that qualified for sure. Getting a proper installation of all the system running your models there, and then you go with a process validation essentially. So you will be running batches, getting data input and output of the system. You are doing the nominal test, stress test, limit test, all the usual suspect of validation. And very importantly, all of that needs to be version control. If you validate a model on version 5 and you have an upgrade, you need to run again. That's all validation.
Thank you, Aurelia. Is there, we hadn't gotten any clarification about the earlier question.
Mhm.
Um, and we are almost out of time. We've got one more question. Martin's just quickly added one in. When you develop digital twin, does it have to come from lab experimental data with design of experiment, or can you use manufacturing data?
All right. So that's a good question because there is a topic of what is considered a validated model. So if you want to validate a model, you need to use data from a GMP source, obviously, because otherwise you can have the data being altered and your output model isn't going to be okay. So when you are planning to validate your model, you need the GMP data. Now, when you develop a model as such, you can tap from everything. There is no particular problem with that. It's just going to be an engineering and a scientific approach. Obviously, you want your data to be robust. That's from a model mathematical equation, but then the entire validation has to come from GMP source data.
Thank you for that. Martin, I hope that that answers your question. If not, please do reach out to us and we will forward that on to the team at Cognizant. So
Yeah.
it's now
Eh,
6:31. I'd like to thank Malaya and Aurelian for your time today and for sharing your expertise with us. I'd like to also thank everyone for joining us this afternoon, and to leave you to get on with your afternoon, evening. As I mentioned before, for those that joined late, this session has been recorded and will be on our ISPE Singapore affiliate YouTube channel, so that you can watch and re-watch that again. And also, if you have any questions, please do let us know. We will forward these on to the Cognizant team. And also, if you would like to get a copy of the slides, we'd be happy to share that too. So, any last words, gentlemen, before we sign off for the evening?
Yeah, thank you very much for joining us. If there are any follow-up questions, right, we would be happy to answer offline, right? Yeah,
Yeah.
that's just we want to say. Thank you again, Arilene.
Thank you. And you can see the details there if you would like to connect with the speakers, but also you can also contact us and we will get you in touch. So with that, I'd like to thank everyone for joining us, and for Cognizant for sharing their expertise with us. Have a lovely evening and a great day to you both.
Thank you.
Thank you. Thank you
Bye.
very much. Bye bye.